Okay, so let's continue with other questions. Okay. Okay, I guess we have stopped here. Here, I think that when the magnetic field is, so we were dealing with the uh, oh gosh, we were dealing with the mean field approximation of the d-dimensionalizing model, and we huh, okay, and we had said that okay, so what you do is that you write down the effective magnetic field, and if you are considering the situation in which Gij is the same, the coupling constant internal magnetic field is the same, so then the where Z is the uh, and we had used the fact that when you are on a periodic lattice and when the coupling constant is the same and the magnetic field is the same, then the system has got translational symmetry. And once you have the translational symmetry, then Sj average is M, not Mg. That is, the average magnetization is the same for every site. It doesn't depend on the site index G. Now, till now we haven't yet defined the mean field approximation. But in the mean field approximation, what one does is that, so let me just write it here. In the so this is up till now it is exact. So this is exact, right? So this is the Ising Hamiltonian. This is the effective magnetic field, and as we have mentioned, this is a random variable. So it's a variable that changes from one microstate to another, and it is this randomness that makes the evaluation of the e to the minus beta h in the partition function a cumbersome task, if not an impossible task. And okay, so I hope you understand the task, right? I mean, once you have the Hamiltonian, then you are supposed to do this summation over SI, which will give you the partition function. Hence, we will obtain the free energy, and then we'll take the derivative with respect to free energy to obtain the average magnetization. But the problem is this is a random variable, and we know how to handle this randomness in the 1D Ising case. We could write it as a product of transfer matrices and this and that. But in 2D, it's utterly cumbersome. In 3D, no one knows how to do the solution. So in the mean field approximation, what one does is the following. Uh, yeah. So in the mean field approximation, what one does is that one approximates this as minus summation over I Si. This is a random variable. So you say that okay, this is a random variable, but I just consider its average value. Instead of taking the actual value, which is a random variable, it changes from one microstate to another. What you do is that you take its you take its average value. So that's why it is called mean field. Mean meaning what? Mean means average. Huh? I hope. the word, this word mean has got many connotations. It has several meanings. I mean, it has several connotations. Probably better to say like that. I mean, mean, you say like, I mean it, or this guy is so mean. And there's another meaning of mean, which is average. Okay, so mean means average. Like mean, median, mode. You must have come across such words in probability theory or statistics. So what you do is that since you are not considering the actual randomness, but you are replacing the actual randomness by the average value or the mean value, and this is already a field, so that's why it's called a mean field approximation. Fine. So in doing so, you are of course making an error. And what is the error? What is it that you are neglecting? You are neglecting the fluctuation. And what is the fluctuation? The fluctuation is HI effective minus HI effective average. This is what you are neglecting. You are saying that, okay, there is some randomness, but let me pretend to be an over smart guy and let me just, consider the average value or the mean value of the field. I will make some error, but let me make some error. Let me make those errors and let's see where do I get to at the end of the day. Okay, so that's what I've written here in the mean field approximation. One neglects deviation. So deviation is another word for fluctuation. Deviation of HI effective from its mean value. That is, you are neglecting the fluctuation. Is this okay? It's an approximation, so there is no. It's an uncontrolled approximation because you do not know a priori whether it is justified to neglect the fluctuation because you do not know the fluctuation a priori. There is no way to know the correctness of the approximation until you have gotten to a point where you have an expression that can be matched against experimental results. At the moment you are doing an approximation, it's an uncontrolled approximation. That's the word that people use just to impress upon the fact that it's an approximation that you don't have an idea of how good it is, how bad it is. It could be utterly nonsensical or it could be very, very good. We'll see. As we go along, you will see how good it is in one dimension, how good it is in two dimensions, and so on. Fine? Is this okay? Yes, no, maybe?
Yes, sir.
Yes.
Okay. So please to speak up, huh? Because, like as I said, I'm not quite yet a god to understand your uh, this thing. So, incidentally, I would like to mention something which is kind of relevant and pertinent at this uh, point, which is that you probably have heard or read about Giorgio Parisi winning the Nobel Prize in Physics. And if you read his Nobel Prize citation, it says that Parisi is being awarded the Nobel Prize for, let me just precisely mention, he did something which is very close to the Ising model, a spin glass model that he found an exact solution of. Let me just mention. This is just to tell you that with your background, you can understand things. I mean, it's not so difficult to. Let me just read out the citation for uh, Parisi. Yeah. So it says the Nobel Prize is being given, one half of the Nobel Prize is being given to Giorgio Parisi for the discovery of the interplay of disorder and fluctuation fluctuations in physical systems from atomic to scale. Discovery of interplay disorder and fluctuations. Fluctuations you already know what it is. Now, hopefully, fluctuation is whenever you have a random variable, there is an average value, and the deviation from the average is what you call fluctuation. And what is disorder? So let me just quickly mention, because he found, the solution is very, very profound and considered one of the cornerstones of statistical mechanics, and he found the solution of that model. So it is not, of course, mentioned categorically. So what is the Ising model? The Ising model is...
Sir, your voice is cracking.
Yeah, but I did not do anything. Again, let me see. You should catch Bunny brothers, maybe the elder brother. Uh, it's better now because my data is fine. Better?
The sounding
I think
faint.
it's a little better. Little better. At least not.
Little better?
Yeah, just keep talking. We'll see.
Okay. And there is an average voice level, and you see this change. Okay.
No,
And
no,
we
it's
hope
it's it's
that
going it's going off. It's going off.
going on. So what do I do? It's not a problem surely with my computer or this thing.
No, I think it's with the internet because your screen also appears a little blurred to me.
My screen also appears as blurred.
I mean,
Still, does it continue to appear blurred or it improve?
yes, I think it's a network problem.
Achha, network. So there are fluctuations. Okay. So hopefully the fluctuations would not blow off at the end of the day. Shall I continue?
What do others say? And can you make out what Shamik is saying, or is it too just like?
Not
Sometimes,
Huh? Sorry? Please.
not clearly
sometimes,
from my end.
No, one of you speak, because if one of you start speaking, then I will not be able to follow. Huh? Sorry? Sorry?
Not clearly from my end.
Acha. But it could be that the problem is at your end, no? What about the others?
Sir, I guess it just
Yeah, it
got
just
better,
got
I
better.
guess.
Yes,
It just got better.
yes.
Okay.
So
Okay,
let's
so
continue.
let's continue. Okay. So the Ising Hamiltonian is, as I told you, the Ising Hamiltonian, the most general form of the Ising Hamiltonian is you do a sum over nearest neighbors, and then there is a Gij, and there's an Si, and there's an Sj. Okay, and of course a special case is when Gij is the same for all, and then you have the simpler Hamiltonian, which is this guy, Si Sj. Okay. Now GIJs, they are numbers that are given to you. Somebody has prescribed that look for the spin on sites I1 and 2, G1, 2 is so. Somebody has given you a table. So let me make some space somewhere and see if I can. I go to paper, maybe that's probably better. It's interesting to know what people have done, and no, not here. Where is paper? Paper. Okay, sorry. Yeah, yeah. So the most generalizing Hamiltonian is which is minus summation over Jij, Si, Sj, Ij. And of course, a simplified situation is this guy. And you can be on 1D lattice or 2D lattice or 3D lattice or 4D lattice, whatever you want. Just 1 minute. Just give me 1 minute. Okay, yeah, fine. Sorry, I just got stuck. But what is the general situation? The general situation is the Gij values are different for different sites. Let's say you are on a one-dimensional lattice, so these are your spins, the lattice sites. And this is 1, 2, 3, 4, etc. And the values are given to you. So suppose somebody has given you a table. Let's say, sorry, I should write here. I should write here Ij, and somebody has given you the values. Let's say 1, 2, Gij is 0.2. 2, 3, Gij is 5.7682. I don't know, some values. 3, 4, 0.2895, and so on. So you see, when you are given a large number of values, then I have told you, whenever you are confronted with a large amount of data, then the best way to visualize the data is to draw a histogram. So what you do is that you draw a histogram. So on this side you would put Gij, and on this side you would put probability Gij. What is the probability that I get a value of Gij between here and here, here and here, and so on? So you will get, and since these are real values, if you have a large number of values, most likely you will get a distribution. Okay, so if you have small number of values, then you get a histogram. When you have a large number of values, then you would get a distribution. So you see that this Gij, in this case, it's a random variable. Why it's a random variable? Because it's different for different lattice size. While here, obviously Gij is equal to J, and therefore no randomness. So this is the delta function case. That here if somebody asks me, hey, what's the probability distribution of Gij? I would say, oh, this is just a delta function, Dirac delta function. While the general cases, there is a randomness. And this distribution could be anything. This distribution could be, the guy who gives me the Gij values, he is the one to decide, what is the distribution like. He may say that, look, these are taken from, I don't know, from Lorentzian distribution or this, that, etc. But, these are random variables. Now for this model, we already discussed in this class, or the previous class, the mean field approximation. So what is the mean field approximation? So let me just go to the next page. So the general situation is the Hamiltonian is minus Ij, Gij, Si, Sj, and then I write it as minus summation over I, Si times Hi effective, where Hi effective is equal to, well, let's say there's no magnetic field, so then Hi effective would be just summation over J. You can add a magnetic field also, it doesn't matter. And then the mean field approximation says that, you replace this random value by, sorry, there's a Gij. I beg your pardon. Yeah. So the mean field approximation says that you replace this random variable by its average value, which is summation over J. Gij is J average, which is summation over J. Jij Mj. This is an approximation. Okay. And what are we after? We want to do this guy to the minus beta h, the partition function, the canonical partition function. Sorry, summation over all Si, from which I will find the free energy, which would be minus kBT log z, from which I will take the derivative. Well, if I want to have the magnetization, I better put a magnetic field to find the derivative of the free energy with respect to the magnetic field, so that I have the magnetization at the end of the day. But the program is well known, what you have to do. But the question is, can I solve this model exactly? Can I find this partition function exactly, given that there is a randomness in the system? Now, randomness, it's a very, I don't know what is the English word for it, but it's not a very, or I know what is the English word for it, but I better not use it. Maybe somebody knows what is the word that I am almost tempted to use for randomness.
Stochastic.
No, something kinky or something. So forget about it.
Okay.
Forget about it. So physicists, they like to give names. So they said, no, randomness, I don't like the word. So they use the word disorder. So they said there's a disorder in the system. Disorder means what? What is the like ordered case? Ordered case is when Gij is the same for all. So this is the the extremely ordered case. The Gij, it's a constant that has the same value for all bonds. So it's very ordered. It's ordered in the sense that think of a class where everybody is sitting on their respective chairs and not doing anything. There is no fluctuation, nothing. So that's the ordered case, and this is the disordered case. Okay, so there is disorder, and of course there is fluctuation. Fluctuation. Why there is fluctuation? Because when you go from one microstate to another, the value of the Hamiltonian will change, and everything changes. So there is disorder and there is fluctuation. Okay, it turns out that this model, this model comes in different guises, but they come under the class of spin glass model. So there is a class of system, they are known as spin glasses. Of course, you know why there is spin in the name, because you deal with spins, and glasses simply because they show extremely slow relaxation to equilibrium. Okay, so glassy behavior is it's a this term you use whenever you come across a system that shows extremely slow relaxation. Okay, so what do I mean by slow relaxation? What I mean by slow relaxation is the following, that I told you that when you go to equilibrium, let's say for this model I plot the magnetization as a function of time. When I am in equilibrium, of course, the magnetization would have a time independent value. But the question is, suppose I prepare this system in some initial microstate, which is not in equilibrium. Okay? And I ask, how long does it take to go to equilibrium? We touched upon these issues while discussing ergodic theory and so on. So you start with some value of magnetization, and in the limit t going to infinity, you go to equilibrium. So this is m in equilibrium. And of course, when you are in equilibrium, the value cannot change any longer with time. So you have a time independent value. But you started with started with a generic initial condition. So like obviously, typically what would happen is your initial condition would change and get to equilibrium. This is what happens when you, for example, boil water in a bowl. That water doesn't start to boil as soon as you keep it in a bowl. You have the water in the bowl and you place it on an oven. What happens is that initially the water sucks in heat from the oven, and the temperature rises, and at some point it gets to equilibrium. And of course, depending on the temperature, it may show a phase transition and so on. So slow relaxation means what? That this time, typically this time is, it doesn't scale with the system size. What does it mean that it doesn't scale with the system size? That this time, let me call it tau. This time, for example, let's say for the case of water, I mean, it's maybe of the order of few minutes or maybe at most a few hours or so. But there are systems that show extremely slow relaxation. They just don't want to relax. It takes a very, 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 very long time. And the worst case scenario is when you have when you have a relaxation time that scales with the system size. So the number of degrees of freedom, let's say in this case you have spins, the larger the number of spins, the longer does it take to relax. And obviously, you are dealing with the system in the thermodynamic limit. So n is very large. So therefore, the system takes infinitely very long time to relax. And this is what you see in glass. The glass meaning the window glass or the glass, the glass that you come across in life, like everyday life. That,
Hello?
yeah,
Hello?
yeah. Hello? Hello?
Sir, we can't hear you.
You can't hear me? So, up till
No,
what point?
I can hear.
The problem in your
Yes, sir.
I think some of us can hear you.
Acha. So, I guess I don't have a way to solve the problem. So, maybe if it is getting recorded in the correct manner, then let me just go and because I don't know what to do. It's surely not a
sir,
problem.
we
with
can hear you. It's the problem in his end.
Acha. So let me continue, and you can view the recording later, or do whatever you want. Okay, so glasses, they have this property that they show extremely slow relaxation to equilibrium. That is, they are not in equilibrium. The glass, the window glass, or the glass that you use to drink water, the glass made of glass, the glass that you use to drink water and so on. I mean, they are not in an equilibrium state, and that's why glass is known as a super cooled liquid, no? Because they are not in an equilibrium state. They are flowing. They are actually not even solid. They are flowing. They are liquid, but they are flowing at a rate which is very, 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 very slow. So slow that you or I, we are unable to detect the flow. We say that, look, glass is solid because I don't see glass flowing like water flows or river flows and so on. Water, solid doesn't flow. That's what we believe, but actually it does flow. And a good revelation of the fact that glass flows can be seen. Like, have you ever been to a very old church? Because unfortunately temples or the mosques, maybe mosques do have, but at least in India, at least in Calcutta, I haven't seen mosques with window panes made of glass. But if you go to a church, a very old church, uh, let's say the Bandel Church or something, so you must have seen that the churches, typically the windows of churches are made from, they have the window pane is made of glass, right? And if you look at the windows of churches, then you would see that there's glass, and you would see that at the bottom of the glass, you would see a thick accumulation of something. It's not dust. It's not dust. And what is it? So it's basically the fact that the glass flows. The glass flows and then it kind of accumulates at the bottom. And why do you see in churches? Because typically churches are very, very old. Let's say in Europe, for example, there are churches that are like, I don't know, like 300 years old or 500 years old and so on. So the glass had enough time to flow. It flows very, 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 very slowly. So such behavior is generically referred to as glassy behavior, slow relaxation. Whenever you see slow relaxation, you say that the system has glassy behavior, and it turns out that this model shows very slow relaxation. It is not a glass; it shows slow relaxation, and therefore it's a model that comes under the class of systems called spin glass. Glass is here used in a loose sense. There is no glass here, but you use glass just to emphasize the fact that the system shows slow relaxation, and you use spin because you deal with spins. Fine. Is this analogy okay? And no, did you know that glass is actually a liquid?
Yes, sir.
You knew that glass is a liquid, but why does it appear solid to us? Simply because it is flowing very, very slowly. Fluid is something that just 1 minute. Okay. Fluid is something that flows. And so if glass is liquid, it ought to flow, and it does flow, excepting that it flows very, very, very sluggish. Like it takes, years, hundreds of years for glass to flow by, let's say, 1 millimeter. Very, very slow, very kind of a very thick fluid. You can think of glycerin or honey. They take a very long time to flow, and glass is worse than that. It takes an even longer time to flow. So therefore, glass is a liquid, and this is a model for spin glass. Up to now, everything is clear, right?
Yes, sir.
And what Giorgio Parisi did was, and I think he was pretty young at that time. At the time when he found, and he could do this calculation, this computation of the partition function for this model. Okay, so this model, it is known as the Sherrington-Kirkpatrick model. David Sherrington was from Cambridge, and Kirkpatrick, I think, was a student, or vice versa. I don't remember. Edwards Anderson model, and so on. So what he did was, Giorgio Parisi could find an exact solution of this model using a trick that came to be later known as the replica trick. And it's considered it was such a difficult model to solve simply because you have randomness, you don't want to do approximation. If you can do approximation, no problem. But the problem with doing approximation is that you can do the approximation, but then you will find that the solutions don't match. So therefore, no point doing approximation for this model. So Giorgio Parisi could do it, and it came to be known as the the method that he used was this replica trick. And so I urge you to look at his papers, because his papers, at least this exact solution of this model, it's not so difficult to read. And of course, he found a very difficult time publishing it, because when he found the solution, people thought that no, it's such a difficult model, you cannot solve it. You must have done some, something. You must have made a mistake. It can't be the solution. So therefore, he had a very difficult time publishing that paper, and I have come to know about it from my Italian collaborators that he did have a very hard time publishing the work, but he eventually published. And since then, people had always hoped and anticipated that he would win the Nobel Prize in physics. But it takes time, because it takes time when you come up with a revolutionary idea. And this replica trick, it's a revolutionary thing. It's a thing that nobody knew about, how to deal with disorder and randomness. And so it took people to appreciate and understand the importance of the trick. And when they did understand, now I think he's 73 years old. So at least if somebody catches you, let's say somebody, in your family catches you and says, look, you are doing an MSc in physics, and what's this Nobel Prize about? What did this guy do? And so, you say that, look, that's what he says, for the discovery of interplay of disorder and fluctuation. You know where the disorder is coming from. The disorder is here. Fluctuation, because it's a statistical system. You go from one microstate to another, there's fluctuation. And of course, this is not one work for which he got the Nobel Prize. He worked in many, many different systems. Amazingly wide variety of systems, from statistical physics to string theory to mathematical physics to quantum mechanics, to particle physics. I mean, if you look at if you go to his homepage and his papers are all listed there, to computer simulations, to econophysics. I mean, all you just name it, and he has worked on it and made very, very important contributions. There's this Alterelli Parisi solution for this. He has done very, very worked on a widest possible variety of problems, not just in one subject, but in physics in general. Okay. And just to wrap up this story, just to give an example of how versatile he could be, I have a friend and a collaborator, Lapo Casetti from Florence, and he had once, about 5-6 years ago, he had, told me about an incident that he was traveling somewhere in a train, and Giorgio Parisi was just behind him. He was, in the train. He was sitting behind him, and Giorgio was traveling with two other physicists. And Lapo told me that I could realize that the two other physicists that Giorgio was traveling with, his co-passengers, one was a particle physicist and the other one was a condensed matter physicist. So, widely different, because particle physics, you deal with the different length scales than condensed matter physicists. And he told me that both of them were asking Giorgio a lot of questions for, asking for clarifications and this and that. And Lapo told me that Giorgio was answering both of them. Like once he was answering the particle physics guy, within a fraction of a second, he would, take up a question from the condensed matter. So he was like, toggling between condensed matter and particle. So he said, it was like a 1 hour or a 2 hours ride in the train, and he was continuously toggling between these two subjects. Once he was answering a very deep question in field theory, particle physics, high energy physics. At the very next moment, he was talking about superconductors and giving an answer to, let's say, some condensed matter magnetism, something, something. So at that time, he said that, it struck him that this guy must be an amazing guy. That how come somebody can on such a fast time scale toggle between two widely different subjects and satisfy the people who were asking him questions. So, and by the way, so he's a professor in Rome at the university which is called La Sapienza, and but if you meet him, I mean, he's a very very down to earth, kind of a bit crazy, like he's lost in his own world. I mean, he may not smile at you, but if you talk to him, he's cordial. He's very cordial and generous and so on. But it's not that he rides a Mercedes Benz and then chauffeur driven Mercedes Benz, nothing of that sort. He just comes by the metro, the Rome metro, and he has a small office, not big office with this and that. And incidentally, this the department where he's a professor boasts of, and this is for Sambit maybe, that it boasts of 3 Boltzmann medalists. In statistical physics, I mean, there is the equivalent of Nobel Prize is the Boltzmann medal. So this Boltzmann medal is considered.
The other two are Galavutti and Jonah Leshini, I think.
Yeah. So it is the only department in the world. So Boltzmann medal is given to somebody who has not won this Nobel Prize. So usually all statistical physicists who have won Nobel Prize eventually had won the Boltzmann medal.
I think the other way of saying it is that Nobel Prize has not been given to. Only a very few statistical physicists have won it. Nobel Committee has neglected the field for many years. So I think Boltzmann medal. It's correct to say that Boltzmann medal is perceived to be the highest.
Highest recognition
that the statistical physicists can win, and most of the Boltzmann medal winners are people who have worked in statistical physics and contributed to it over years.
I think did Lars Onsager get it? Maybe not.
I'll have to check.
No, maybe
I'll have
not.
to check.
Because the first winner of Boltzmann medal was Wilson, who eventually got the
Hmm.
Nobel Prize, and I guess Giorgio Parisi is the second one. He got Boltzmann medal long ago.
Who else won? De, De, did Dejon get? I don't know.
No.
Check.
Dijon, Dijon didn't get Boltzmann medal.
Boltzmann
Did
medal.
he? Did he? I am not sure.
I'll check. Just give me a minute.
No, I don't think.
But there are, I mean, but, like, apart from Parisi, so Jonah Lassigno also came very close to winning a Nobel Prize. This was, I
Well,
think,
why
for
I think
all the particle physics prizes.
he was almost. I mean, there with the exact solution of the. I mean, not the solution, the renormalization group idea, but he missed out at the last step. I mean, he could not get something correctly, and so no, so he didn't. This Dijen didn't get. He got the Nobel Prize. He didn't get
Yeah,
Boltzmann medal.
yes,
Dijen,
Dejon has not won.
Dijen.
I think it's only, yeah,
I think Lars von
it's only
Sable's time it was not there because the first time the prize was awarded was in
75.
1975. So which is
75.
but anyway, so we come back to mean field
No, but
approximation.
amongst the Italians, it is a. I mean, I think Jonah Lassigno and also Cabibo, who was a
Yeah,
Parisi's
Cabibo.
teacher, their
Yeah.
exclusion was very notorious because I think there were two particle physics prizes won, and they were both. I mean, their collaborators won.
Yeah.
Whereas they did. So the Italians for many years have, I mean, they felt that the Nobel Committee has been against them. So they are very happy about
Yeah. That is true.
Parisi.
That Nicola Cabibo. I think he was he passed away in 2010, as late as 2010. And I think this is the sixth Nobel for Italy or something, no? In
Yeah,
physics.
okay, I don't. Yeah, I don't
Yeah,
know.
that's what I read somewhere.
But most of these people have done particle physics as well as statistical mechanics.
Yeah, definitely.
Cabibo, Jonah Lassigno, Galavotti, Parisi also.
Galavotti was more from mathematical physics, I would say.
Okay.
Galavotti is not particle physics guy, he is more from math.
But
But anyway, so just to come back to the statistical physics thing, so at least I mean when you are in the subject and when a prize is awarded in this subject, I mean it's good to know what is it all about and so on. So this was this, and the other half was given to uh, the Sukuro Manabe and Klaus Hesselmann for something to do with climate. I mean, climatologists. So both of them are climatologists, and one is from the Sukuro is a Japanese settled in America, I guess, and Klaus Hasselmann is from Germany. So America, Germany, and Italy.
so Parisi has worked on climate also.
Yeah, he has worked on almost everything.
Even if they didn't cite him,
Yeah.
I have a feeling that this like the whole prize went for climate change, but maybe the committee felt that they could not ignore Parisi's like spin glass work
Ha.
because it's much more well known than his climate work.
Yeah, I mean this Hesselman, I seem to know his work, but it is, I mean, at least some idea, but not the other guy, the Sukuro Manabe. Anyways, okay. So was that helpful or was that nonsensical? Did you like it that whenever a prize is given, it's not necessarily given to a problem that is completely out of the world, like you don't know what the problem is all about. Prize is always given to a simple problem for which, and you usually in physics, simple problems are the most difficult ones to solve. Complicated problems can be solved in one way or another, but simple problems are very difficult to solve. And so, therefore, you see that, like even you can understand whatever it was about. So, was that helpful or was that, useless?
Yeah, it was helpful.
Okay. So, okay, so we come back to the mean fieldizing model. So we will not, of course, do the like Parisi's like solution, this replica trick. So I think now, I think this year no, last year he even published a book, Cambridge University, some spin glass something. I haven't read that book, so I just came to know about it recently. Anyways, okay. So therefore, what is the mean field approximated Hamiltonian? So I started off with the Hamiltonian, which was this minus j si sj I, and the mean field approximated, which is nothing but minus summation over I j. Sorry. Let me keep the magnetic field also, because otherwise you will not. I started off with the Hamiltonian H is equal to minus summation ij j si sj minus, well, j you can pull out, okay, psi. I told you that this you can trivially write as summation over I si times hi effective. Then I told you that this is a random variable, so you approximate it, you write it as minus summation I si of hi effective average. And hi effective average is what? This is h plus jzm. Fine.
Yes.
So this is the mean field Hamiltonian. This is the approximated Hamiltonian. Right? This is the approximated Hamiltonian, not the actual Hamiltonian, because we are doing an approximation. Now, if I look at this Hamiltonian, the first thing that strikes you is that you have a sum over I, but you don't have a sum over G. So that interaction seems to be missing. It has simply disappeared in doing this approximation. It seems like I have spins which are independent, and each spin is feeling the same field H plus JZM, right? That's why you have a summation over I SI, but there is no SJ term anywhere, right?
Yes.
So the spins appear to be effectively non-interacting. Why effectively non-interacting? Actually, they are interacting. We will see how the interaction, see this interaction part is kind of, it has not really disappeared. You know, this term, it really came from the sum over J of, is J average. This part, it came from there, right? I mean, this whole part, it came from there. It has not disappeared. It has just it is just appearing in disguise. Huh? It has kind of put on a mask. A mask over his whole face, that his face can no longer be recognized. You know, he cannot be recognized, but he is there. He has not absolutely disappeared. So that's why we say effectively non-interacting. Clear that it is not exactly non-interacting, it is only effectively non-interacting. Fine.
Yes.
Okay. So now, since the spins are effectively non-interacting, I know how to solve the magnetization, the average magnetization for the ith spin using this Hamiltonian. So let me just do it. Sorry. Let me get rid of this. Yes. And let me solve this one. So I want to know the average magnetization for the jth spin, which is by definition m. And how do I find the average magnetization? The same trick, summation over SI. where I is here, of course, it's a random variable, Sj times exponential of minus beta h, and this is my approximated Hamiltonian. So minus beta, so that minus sign will give you plus beta summation over I Si h plus jzm divided by this, right? So this is the partition function in the mean field approximation, and this is the usual way to find the average value of a random variable. Fine. This is clear?
Yes.
Yes.
Okay. Now something strange will happen, not strange, something simplification will happen. You see, in this sum, there is no cross term. There is no SI term. You have just summation over I SI. Here also you have summation over I SI. So if I write it out fully, the numerator and the denominator, there are certain terms which are going to cancel, right? What will happen is that when I write it out fully, then I will get terms like e to the power minus beta S1 H plus JZM e to the power beta S2 of same factor H plus JZM and so on, right? And somewhere here is this Sj sitting, and I have summation over all the Si, right? This is the numerator. Fine.
Yes, sir.
Okay. And what is the denominator? The denominator will be again summation over Si, and then you have e to the power beta S1 H plus JZM, e to the power beta S2 H plus JZM, etc. Dot, dot. Fine.
Yes, sir.
Now you will see that all terms in the numerator and the denominator that do not contain Sj will cancel. Right? For example, this term e to the power beta is this term will cancel with this one term, this term will cancel with this one. The only term that would not cancel is this term, whatever I've written here, summation over Sj e to the power beta Sj H plus JZM Sj, and in the denominator you would have, this is G, summation over Sj exponential beta Sj H plus JZM. Fine.
Yes, sir.
Can you repeat once again the last line?
This line, no, look at the numerator and the denominator. Which term will not cancel? The term that will not cancel is the term that contains a j here, Sj here, right? So that term is what? Exponential beta Sj H plus JZM Sj summation over only Sj divided by this. Why it doesn't cancel? Because of the term here, Sj.
Oh, okay, sir. Okay.
It's a trivial thing, no? That the same factor. So you have to remember one thing. When I write summation over Si, this is same as writing summation over S1, summation over S2, summation over S3, right?
Yes, sir.
So therefore, when you are doing the summation, all terms from numerator and denominator will cancel, excepting the term pertaining to the spin J. Right?
Yes, sir.
Please stare at it for a minute and let me know if it makes sense. It's okay?
Okay, sir.
Okay. Now let me do this sum. This sum is quite easy to do. Sj can take only two values. So I put Sj equal to plus 1. When I put Sj equal to plus 1, so I have plus 1 times e to the power beta of H plus JZM, which is this term. Sj can have the other value -1. When you have -1, you have -1 times e to the minus beta h plus jzm. Fine, that's a numerator. Right? And the
Yes, sir.
denominator would be similarly e to the beta h plus jzm plus e to the minus beta h plus jzm. So you have e to the power x minus e to the power minus x by e to the power x plus e to the power minus x, which is just tang of beta plus jzm. Sorry, it just got cut. Tang of beta h plus jzm. Fine. So I get an equation m equal to tan hyperbolic beta h plus jzm. Must be doing it in magnetization, but anyways, so you get this equation. M is equal to tan hyperbolic beta h plus jzm. Fine. Please understand that this is an approximate answer. This is not the actual Hamiltonian. We did an approximation. We neglected the fluctuations, and only when you neglect the fluctuations that you come across, that you end up with this equation. If you had not done the approximation, you would not have been able to obtain an equation of this sort. Fine.
Yes, sir.
Okay. So at this point, let me take a break for 10 minutes. It's 12:35. So let's come back at 12:45, 10 minutes, and then we resume and then we see what we get out of it. Okay?
Okay.
Okay, sir.
Okay, thank you. Hello?
Yes, we can hear you.
Okay. I guess the others are also back.
I think it is 18 people now.
Yes, yes.
Okay, fine. So this is the equation that we get. Now let us ask, what is this M? M, you remember, M was the average magnetization for the jth spin. So M, sorry. So M is the quantity that, or the average magnetization for the jth spin, which is same as the average magnetization for the whole system, because you remember that the this is same as 1 over n summation over I equal to 1 to n of Si. You're right. I mean, it is the same. So this is the average magnetization. Now, before I proceed, let me give you a general notion of how to write an equation, which probably you know, probably you don't know. So, an equation has got, as we all know, an equation has two sides, a left hand side and a right hand side. And the general philosophy behind writing the equation is to say that, okay, so there's a left hand side and there is a right hand side, and the equation has this form. Now, an equation has this structure, general structure, that the right hand side is known and the left hand side is given in terms of the right hand side through the equation. Let's look at an example. Let's say you say fx is equal to sine x. It means sine x is known, and what is f of x? F of x is equal to sine of x. You don't or let's say y is equal to x square. That means x square, this is the known, meaning what? That this is the independent variable. On the right hand side, you always have the independent variable, the value of which you know beforehand. That is, this is the value that you assign. You say x is equal to 2, and then you ask what is the value of y? Y is x square, which is 4. So the right hand side is always known because it is the independent variable, and the left hand side is what comes out of it. That's the general notion behind writing an equation. You never write an equation the other way around, right? An equation has always a left and a right hand side. Right hand side is what is given to you, and left hand side is what comes out of it. Okay, is this known to you generally? So you never write an equation like this. Sin x is equal to f of x. I could have written it because when a is equal to b, then b is always equal to a. The same thing. But this is a wrong way of writing, because it says the right hand side should always be the thing that you know, that is the independent variable. F of x is not the independent variable, x is the independent variable. So therefore sin x is the x is the independent variable, and therefore sin x is what you assign, and then f of x is equal to sin of x, right? So this you know, right? Hopefully you know. I don't know. Yes, no, maybe.
Yes, sir.
Okay. So, but then now we have a strange situation that M is the quantity that I ought to have known, because M is appearing in the right hand side. M I ought to have known, but M is the quantity that is also the unknown, because it is appearing on the left hand side as well. So such an equation is known as a self-consistent equation. The quantity that you are trying to find is appearing on both sides of the equation. So that means M has to be found self-consistently. What does it mean? I'll explain in a minute. Has to be found self-consistently. So it's a it's a feature of mean field approximation, and it's transcendental equations at this point. That m is the quantity that you assign from outside. You say m is equal to 5. You put m equal to 5 here. You should get back m equal to 5 from the equation. If not, then you have guessed a wrong value for m. Okay? So forget about this equation. Let's look at this equation. Tan x, let's say tan x minus x equal to, so tan x is equal to x. So x is the independent variable. So I give a independent variable, meaning it is in my hand. I give a value to x. Let's say I say x is equal to 0.5. Then I should get tan of 0.5 should also be equal to 0.5. If not, and surely it is not, then this is not a solution of this equation. So that is what it means to solve an equation self-consistently. That you assign a value to the independent variable that is appearing on the right hand side, and the left hand side should give back the same value. If not, then you have not been able to solve the equation. And such a method of solving the equation is known as finding the solution self-consistently. It is consistent with itself. Okay?
Yes, sir.
So this is a generic feature of all mean field approximation schemes. This mean field approximation scheme appears in different avatars in like other fields of physics. For example, in quantum field theory, in condensed matter physics, there you have the Hartree-Fock approximation, the Rudolph-Piles approximation. So they are all ramifications of the same basic technique. So mean field approximation is somebody catches you and says, look, hey, what's a mean field approximation? So you say the basic feature of mean field approximation is you replace a randomness that's present in the system by its average value of the mean value. That's it. That is the crux of the matter. Then there are details that have to be worked out and so on. And obviously, in different systems, you will come across different equations. But the crux of the matter is that you have a randomness in the system. You replace the randomness by its mean value. And obviously, when you replace the randomness by its mean value, you are neglecting the fluctuation. So mean field approximation means neglect of fluctuations in the system. Okay? That's it. Nothing more. It's an uncontrolled approximation because when you neglect something, typically in life as well as in generally when you neglect something, you know what you are neglecting. You say, okay, this is 2.000078. Let me neglect that 0.00078 and call it 2. So you know what you are neglecting. But here, unfortunately, you do not know quantitatively what you are neglecting. Qualitatively, you know what you are neglecting is you are neglecting the value, the random value from its average value. This is what you are neglecting. But when you are neglecting, you do not know a priori in terms of numbers, what is the value of this guy? So when you are neglecting, is it 0.02 that you are neglecting or 10 that you are neglecting? You don't know. So that's why it's called an uncontrolled approximation. And the signature of a mean field approximation, please.
Should it be called a fluctuation that is averaged over or fluctuation that is neglected?
Fluctuation that is neglected. It is not averaged over. If the fluctuations got averaged over, then the mean field approximation would have been exact. Then, I beg your pardon, then you don't call it an approximation. You call it a mean field, an exactly solvable method. And in fact, there are systems where mean field approximation is not an approximation, it is an exact. So this fluctuation, there are situations where this fluctuation is exactly equal to 0. There are special systems. But generally...
Okay, so So
please.
if some system is in equilibrium and somehow I am with some external force I'm perturbing the system, so so it will be out of equilibrium. So in
Yes.
that case, how can I say that we are ignoring the perturbation and not summing over that or something averaged over like on the perturbation? So how can we tell that the mean field approximation will give the correct resolution to this?
Okay. You are asking a very different question. Okay. Okay. But let me draw a picture to tell you, you know, to pictorially depict what you have in mind, and then you tell me whether I am right or wrong. So you have this magnetization as a function of time. Okay. Now, like initially, the system is in equilibrium. Okay, the system is in equilibrium, meaning that there is an average magnetization. So let me use the symbol curly m, because I was using curly m to show the microstate dependent magnetization, right? So this is the microstate dependent magnetization, which has got an average value. The system is in equilibrium, so this is my m. The system is in equilibrium. This is time 0, this is time minus infinity, and the actual value is fluctuating about it, right? Fine.
Yes, yes.
The system is in equilibrium, meaning, and you remember that equilibrium means macroscopic observables should not depend on time, and this average magnetization is a macroscopic observable. Macroscopic, why? Because it sums over all the spins, and it's an observable because you have averaged over microstates. You cannot obtain experimentally microstate dependent values. You always get values which are already averaged over microstates, so it is fluctuating. Fine. Now at this stage, if you say what is my mean field approximation, I would say mean field approximation is to say that this curly m is equal to m. This would be the mean field approximation at this stage. Okay. It could be wrong, it could be
Yes.
right. Whether it is wrong or right depends on the level of fluctuations, right? If the level of fluctuations, if let's say so this average value, if let's say this average value is 0.7 and this fluctuation level is let's say one order less, let's say of the order of 0.0012 orders less, then I can say, okay, come on, I mean small fluctuation. Fine, at this level. There is no field anything outside. Huh? Force, so what you are saying a force. Okay.
Yes.
Okay.
So it's like doing equilibrium statistical mechanics till now, right?
Yeah, till now I am doing equilibrium statistical mechanics.
Okay.
So I had started with an initial condition, I let the system evolve, I get to stationary state, which is equilibrium, and now I apply a force. Okay. And by the way, this situation, it could have been true. I mean, this would be true even if there is an external magnetic field, but a time independent magnetic field, right? There's a time independent magnetic field, and that will determine the magnetization, right? Because the magnetization can be induced both in presence as well as in absence of a magnetic field if you are dealing with a real magnet. Fine?
Yes.
So let me concomitant with this figure, let me draw a figure for the magnetic field. Where do I draw? Acha, here maybe. Let's say to make you feel happy, this is the external magnetic field. Let me put a subscript external, like this thing. This is my time, this is 0. And let's say there was no magnetic field in this region, minus infinity to 0. Here there was no magnetic. Now you say you are turning on a magnetic field to drive the system out of equilibrium, right? So let's say you turn on a magnetic field that is changing as a function of time. According to some, so H external is like, I don't know, it is increasing as a power law or something, fine?
Yes.
Obviously the system was in equilibrium, and now when you have turned on a magnetic field, that is changing with time, the system will go out of equilibrium because you have applied something externally that itself is changing. So what the system will do is that this was the average value in the absence of the magnetic field. This will also, this average value would also start changing as a function of time, and the fluctuations would also do this thing. Fine.
Yes.
Here, of course, the system is not, as you correctly pointed out, it is not in equilibrium. Why it is not in equilibrium? Because the average value is changing. If I make a measurement, I'll find that the average, the measured value is changing as a function of time. Right? So here the
Yes.
system is not in equilibrium because the external force is changing, external field is changing. Now your question is, if I can do mean field approximation here. Is
Yes.
that the question?
Yes.
Here it could be very dangerous. Here, you see, here one advantage is that the average is time independent. So I am measuring the fluctuation with respect to a time independent value. Right? So the fluctuation here and here. But here the average itself is changing as a function of time. So my base level, the level with respect to which I measure my fluctuation, is itself changing as a function of time. So I may be able to do this mean field approximation. I may not be able to do this mean field approximation. Why? What is the situation in which I cannot make this mean field approximation? Suppose it does like this. Nobody has told me that the system has to behave. So this is my average, and the fluctuation will be about the average, but nobody has told me that the fluctuation will be small. So the system, what may do, and typically that's what it does like this. Why does it do like this? Because the system suddenly feels a jerk. The system was happily sleeping here. There was no field, the magnetization was zero. And suddenly you turned on the magnetic field. The system gets a shock. My goodness, what is happening? And then the system slowly understands, look, there is a time independent, there's a time dependent magnetic field. Okay, let me relax, calm down, and so on. So surely in this jerky situation, you cannot do mean field approach. You can always do, but it will give you some incorrect answer.
Okay.
You got this point of jerk, right? That, say it's like, think of the following situation, that you are sleeping, and then somebody comes and, the kosher example that comes to my mind is that, let's say on a sunny afternoon, winter afternoon, you are relaxing, and then almost half sleep and then half asleep, and then somebody comes close to you and shouts into your ears, boo! And then as soon as you hear the sound, you get a shock, like your heart starts pumping at a fast rate, and then after some time you realize, oh, it's you. Okay, I thought, okay, what has happened? Something. Huh? So it's a similar situation that you get this jerky, and then things. It may relax, it may not relax. I mean, for glassy system, it doesn't relax. It will continue. Oops, sorry. Where are we? Yeah. It continue to show this jerky behavior. It doesn't take, the fluctuations do not tame down so like easily in time. Depends on the situation.
Okay, so one more question, that is the time scale of this jar that is happening in the system will depend on the external force somehow?
Yes, of course. Suppose your external field is not so much, but it is, let's say, this. Very, 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 very mild. Think of that boo example, that somebody shouts into your ears, boo! And then you get, you get a shock or something. And somebody comes and says, boo, I say, okay, nothing more. So then the field will do like this, and you'll get some small fluctuation. And in fact, this small fluctuation is it is the regime of there's a theory which is known as the linear response theory, where the field that you turn on is a very mild field. It's not like 10 Tesla. It's maybe 0.8 Tesla. Think of that Boo example. Somebody comes and whispers, says, "You are Shonok, right?"
Yes.
So I will say, "Hey, Shonok." I say, "Okay, come on." And then instead, what is the other example? Someone says, shouts your name, and then, okay?
Yes. Yes. Got it. Right.
Okay. So, of course, the time scale will depend on how strong is the external perturbation. Force is not the right thing to talk about here. I mean, the generic term is perturbation. You are perturbing the field. You are disturbing the system was in equilibrium, and now you are bringing about some disturbance. And the question is, how long? A good example is, suppose you have since I don't know whether you are in the hostel or but you must have seen, this is a generic thing to see, that suppose you look at the surface of water in the sea or the ocean or the river Ganges, let's say. Okay, so there are ripples. So if I look at the surface of water, I mean there are ripples, but then there is an average height. Okay, and let's say let's say a ship passes by, and you must have seen that what does the ship do? The ship would generate waves that would travel across the ocean or the water body. And then after some time, of course, I mean, if you wait, let's say for 10 minutes, depending on the size of the ship, that the things would just be relaxed. Okay, but it depends. Like if it's a small boat or a ship, it makes a difference. Or suppose you throw up pebble into the water, it will cause some fluctuation, but those are they would go away. I mean, this jerky thing will not last for long. Fine.
Yes. Yes. Right.
Okay. So this linear response theory, of course, it's not there in your syllabus, so therefore I will not do it. But if you want, you can look up this linear response theory was developed by a Japanese physicist called Kubo, R. Kubo. He has a statistical physics book also, and he has an article. It's called the fluctuation dissipation theorem. It's a journal is Progress in Theoretical Physics, I think. An article from 70s where he developed, I think. Yeah, is there a question? No question. Okay. So you understand that this is a special kind of equation. It's a self-consistent equation. This is what I want to find, which is appearing both on the left and on the right hand side. Okay. So how do I solve this equation numerically? I know that M being a magnetization can take a value only between -1 and +1. So I assign a value of -1. So what I do is that I assign a value. Let's say I say M is equal to -0.8. Then I know for the given model, I know all these constants, beta, h, jz, etc. I find this function. So now I find the left hand side, and the left hand side should also give me back the same value. If I get the same value, then I say my guess was correct. The solution to this equation is M equal to 0.8. If not, then my guess is wrong. I try again, say 0.235. Does the left hand side give me back the same value? No, it gives me 2.862. 0.286. Wrong. Okay. So it's a self-consistent equation. Fine.
Yes.
So what is the way to solve this equation? That whenever you have two things that you are trying to match, the best thing to do is to plot. And like again, you have done this thing, I guess, but let me just quickly get over. I know that this system, this Ising system, it shows a phase transition when there is no magnetic field. So let me just go to the case where there is no magnetic field and try to obtain the value of the transition temperature. Sorry. Oh. So I put H equal to 0. So this is the equation. This is a transcendental equation. Okay. How to solve this equation? One way I told you, you can always write a numerical program to say, okay, I input m equal to 0.8, output should also be m equal to 0.8. If not, I try again. So it's in the same vein as, let's say, the Newton-Raphson method of finding the roots of an equation, the same vein. You know this Newton-Raphson method of finding the roots of an equation, no? You make a guess and you should get back the same value. If not, then you keep on trying. You know or you don't know?
No.
Do you know?
Yes, sir.
But why are you so mild? You shout. Yes, I know. Okay. So how do you solve this equation? What you do is that you plot the left hand side as a function of m, you plot the right hand side as a function of m. So m as a function of m will give you this straight line. This is m as a function of m. And tan hyperbolic beta jzm, tan hyperbolic beta zjm as a function of m, what does it look like? Well, I know tan hyperbolic function has this property. Then when the argument goes to plus infinity, tan should go to plus 1. And when the argument goes to minus infinity, tan should go to minus 1. So therefore, I have this this one. You know, at plus infinity, you know, there is a catch, and I'll ask you about that catch soon. But let me just. Some of you who are careful enough will catch me at once as I say this, but let's see whether you are able to catch me or not. But anyways, when m goes to plus infinity, it goes here. When it goes to minus infinity, it goes to minus 1. Fine? But I have to be careful. What is the slope? A function, it can go to plus 1 or minus 1 in 10 different ways. It can go in a very sluggish way, or it can go like this, or it can go very sharply. All are possible, right? Fine?
Yes, sir.
So that will depend on, so how to determine? How to determine, whether tan hyperbolic beta jzm, it goes to m like this or like this or like this. What is the simplest way? Simplest way is to find the derivative at m equal to 0 here. If the derivative is here or here or here, that will tell me whether it wants to go there as a fast function or as a slow function. Fine?
Yes.
So how to find the derivative? See, I want to know the derivative here at m equal to 0. So when m is equal to 0, I want to know the derivative here at m equal to 0. So what I do is that when m is very small, then tan hyperbolic x, I know what it is. It is x minus x cubed by 3, right? Fine?
Yes.
So therefore,
Yes.
tan hyperbolic close to m, well, I can even make it's approximately equal to beta jzm as m goes to 0. Fine?
Yes, sir.
So therefore, what is the slope? What is the slope at the origin? Can somebody tell me what is the slope at the origin? Slope at the origin of this function?
45 degrees.
No, come on. What is the slope of this function? beta zj, right? Slope means what? You take the derivative. So if you take the derivative with respect to m, you get beta jz. How do you get 45 degree? 45 degree is the slope of this line. M is equal to m. This line. This line has angle 45 degree, but not this one, no?
Okay, sorry, sir.
Right. Let me get rid of this. So this is the slope at the like origin. Okay. So now you see that whether it would go as a sharp function or as a slow function depends on the temperature, because Jz are given to you. Z is the value for the lattice that you are working with, 1D lattice or 2D lattice. J is given to you. So therefore, depending on beta, the slope can be, greater than 1 or smaller than 1, right? I mean, this number, it can be larger than 1 or it can be smaller than 1, right? Fine.
Yes.
Now let's look at the situation where the slope is small, or it can be equal to 1. That it is also possible, right?
Yeah.
Fine.
Yes, sir.
Okay. Now let's look at the case where the slope is smaller than 1. See, this curve has slope equal to 1, right? M is equal to m, y is equal to x. That has a slope 1. So this curve has a slope equal to 1. So if beta jz has a value smaller than 1, that means the curve is going to be this one, right? Because this curve will have a slope which is smaller than 1. Fine. Here the slope is smaller than 1, right?
Yes.
What is the other situation? When beta jz has a value larger than 1, that means the slope is larger than 1, then the curve will be this one. Let me use a different color maybe. Fine?
Yes.
Fine? Fine? And
Yes, sir.
what is the last situation when beta jz has a value exactly equal to 1? Then the curve is going to merge with this straight line here, and then it would do like this. These are the only three possibilities. Fine?
So beta zj equal to 1 corresponds to t equal to tc curve.
No. I don't rush. I'll come to it. Don't worry.
Okay.
Huh? Don't worry. मैं हूँ ना, so you wait.
Sir, hello.
हाँ.
Hello.
Sorry.
Sir, can you please once again repeat the last part? When plus 1 and minus negative 1, less than 1.
Okay. So, sorry. What am I doing? I'm choosing the wrong one, I guess. Slope at the origin, sorry, is equal to beta jz. This is okay?
Yes, sir.
Now, beta jz, there are three possibilities. Beta jz less than 1, beta jz equal to 1, beta jz greater than 1. Fine? These are the three possibilities.
Sir, how these three possibility come? And I want to say that how can I say that beta jj greater than 1 and less than 1?
See, at large value, it has to merge with it, this one, right? So, when you are thinking about a slope, these are the only three possibilities, right? You cannot have a divergence. Why you cannot have a divergence? Because if the curve is diverging here at the like origin, then it cannot saturate to finite values as m goes to plus minus infinity, right?
Yes, sir.
Okay, so it will have a finite value, right?
Okay.
it cannot go to, it can be 0, no problem. That is taken care of here. But it cannot be infinity. Why it cannot be infinity? Because a curve that has got infinite slope here, it cannot saturate to finite values as m goes to plus minus infinity, right?
Okay, okay, sir.
Okay. Okay.
Okay.
Now let's look at, so what is the equation that I'm plotting? So I'm plotting m and I'm plotting tan hyperbolic beta jzm, these two equations. So m I have already plotted. M is this line. M is equal to m. This is a line that has slope equal to 1, right? If you plot x as a function of x, the slope is 1, right? Because dx is 1, right?
Yes, sir.
Okay, so this is now one possibility is, now let's plot the second function, tan hyperbolic beta jzm. Tan hyperbolic beta jzm, I can blindly, I can close my eyes and say, look, when m goes to plus infinity, it has to go to 1. Doesn't matter what you do, because that's a property of tan hyperbolic function. The curve here has to have the value plus 1, here has to have the value minus 1. Fine. That I cannot do anything. Fine.
Yes, sir. Yes.
Okay. So you keep your mic on and you continue saying yes, yes, or no, no, whatever is the situation, so that we are in, we are in synchrony. Now, let's say when beta jz is less than 1. Less than 1 meaning, so what is beta jz? It is the slope at the origin. That means at the origin, I should draw a straight line. And by the way, this is a straight line, right? It is close to the origin. Tan hyperbolic is a straight line, right? As a function of m.
Yes, sir.
So close to the origin, I should draw a straight line that has a slope smaller than 1. That is, the angle is less than 45 degrees, right? So therefore, the curve will be this one. Here it is linear and has a slope, because this one has the slope 1. So therefore, this one has a slope smaller than 1. Fine?
Okay, sir. Okay.
Okay. What is the other possibility? When beta jz is larger than 1, that means I should draw a straight line here that has a slope, an angle made with the x-axis. That angle has to be larger than 45 degrees. So this is the possibility. The asymptotic values are given. I cannot play with it. Fine?
Okay, okay, sir.
And therefore, what is the case when beta jz equal to 1? Then I have a curve. Let me draw this one. I have a curve that is matching, that is coinciding with this straight line, and then doing it this way. Fine?
Yes, sir.
Crystal clear, right?
Yes, sir. Yes, sir. Now it's clear.
Okay. So therefore, I have 3 possibilities for the tan hyperbolic function, and I have just one possibility for the m function. Oh, sorry. Now let us look at, see, I want to solve this equation. Why am I choosing the wrong? I have to solve the equation m is equal to tan hyperbolic beta jzm. So therefore, I must find the self-consistent solution. Self-consistent solution meaning an m that satisfies the left-hand side as well as the right-hand side. That is to say, I have to find the intersection of these two curves, right? Right?
Yes, sir.
So look at this curve. This is for the case when beta jz was smaller than 1. This was for the case when beta jz is smaller than 1. So I have to find the intersection between this curve and this curve, M. This is a straight line. This curve has just one intersection point, 0, right? Right?
So can you please repeat once again?
This curve, look at this curve. This curve is for beta jz smaller than 1. This curve and the curve m equal to m, this curve, has got just one common intersection, which is m equal to 0.
Yes, sir. Yes, sir.
So, m equal to 0 is the solution if beta jz is smaller than 1. Happy?
Okay, sir.
What about the case when beta jz is larger than 1? Then the curve is this one. Well, there will be many curves, but you know, whenever beta jz is larger than 1, then the curve would have to lie like above this curve, right? Whenever beta jz is larger than 1, then the curve would have to lie above. So that means this is going to be the curve. Fine?
Yes, sir.
So how many intersections is there? 1,
3.
2, 3. So therefore, there are m equal to 0 and m equal to plus minus some number. Let me call it like ms. These are the solution when beta jz is larger than 1. Fine?
Yes, sir.
And what happens when beta jz is equal to 1? Then also you will have just, so beta, let me get rid of these things. When beta jz is equal to 1, so this is the curve for beta jz equal to 1. Sorry, this is the curve. Sorry. And intersection of this with the straight line is again 1. So therefore m equal to 0, this is the only solution when beta jz is equal to 1. Fine?
Yes, sir.
So you see that this equation, this may have 3 solutions provided beta jz is larger than 1. 3 solutions. Like otherwise it has just one solution, m equal to 0. Fine?
Yes, sir.
And when is the change taking place? The change is taking place exactly when beta jz is equal to 1. Look at here.
Sir, hello.
Hmm.
Sir, I have a question. When
Hmm.
beta jz greater than 1,
Mm-hmm.
then we get m equals to 0 and m equals to another
Yeah,
point.
absolutely, absolutely.
Sir, here to another points means the coordinate point, or I think m equals to 0 is the origin. Then what is m equals to ms? What does?
This value. Intersection point here. This is the intersection point. This one
Okay, okay, okay,
and this one.
okay, okay, sir.
Right? Intersection point. X value.
Yes, sir. Yes, sir. Okay, okay, sir. Got it.
Right? So you have 3 solutions when beta jz is greater than 1. One solution when beta jz less than equal to 1. Mhm.
Yes, sir.
It doesn't tell me anything about phase transition. Those of you who are familiar with bifurcation theory would just say that, look, it's an equation that has one solution in one parameter regime and three solutions in another parameter regime. Most likely there is a bifurcation of some sort that is happening. When it is happening, change happening at beta jz equal to 1, right? Exactly at beta jz equal to 1, a change is happening. We cannot say anything about phase transition here, because phase transition is much more complicated. I have to look at the free energy, I have to take the derivative, I have to find that the first derivative diverges, then I call it a first order. If the second derivative diverges, then I call it a second order. Here I haven't done anything. I've just found a solution to a transcendental equation. Fine?
Yes.
Sir, why you say that change happening at beta jz equals to 1?
Look at this one.
Oh, okay. From the graph, can you say
Yes, of course, I can say. Let me say it in the graph. I can do anything you like, more or less. Huh? Shaktiman, so I can do anything. When beta jz was larger than 1, there was one root here and there was one root here. This is minus ma, this is plus ma. As beta jz is approaching 1, these two roots, they start approaching the 0 and they bump into one another. Again, those of you who have done bifurcation, you would say, look, there's something that you see when you have annihilation, pair annihilation, right? There were three roots. When beta jz was larger than 1, one root, two root, third root. As beta jz approaches 1 and becomes smaller than, as beta jz approaches 1 from above, then these two roots, they start approaching, they come closer, closer, closer. At some point, they just annihilate and become one, only one root. Fine?
okay, sir, I understand, sir.
And when is it happening? It is happening exactly when beta jz equal to 1. Because above beta jz, below beta jz equal to 1, you always have one root, namely m equal to 0.
Yes, sir.
So you see so jz cannot change because jz are given to you. You are given a three-dimensional lattice, so z is 6. You cannot change it as a function of time or whatever, time or whatever. J is given to you, J. This is the coupling value given to you. You cannot change. What you can change is the temperature. And what you see is that when you are changing the temperature, you either have three solutions or you have one solution. That means you take your system, your magnet, you keep it at a temperature. If the temperature is such that beta jz is larger than 1, you have three possible values of the magnetization within the mean field approximation. If the temperature is such that beta jz is smaller than or equal to 1, you have only one possible solution for the equilibrium magnetization, namely m equal to 0. Fine?
Yes, sir.
So beta jz equal to 1, it marks a very specific temperature or beta c. So beta jz equal to 1, this is an equation. If you solve it, you get beta c equal to 1 by jz. This is a very specific temperature on either side of which you see a different behavior. That is when beta jz is larger than 1, that is when, so beta c is equal to 1 by jz, that means your tc, which will be, beta, this is nothing but 1 by kb tc. So tc will be,
jz by k beta.
yeah, exactly. So when T is smaller than Tc, then you have three solutions. Fine. T smaller than Tc meaning beta larger than beta c, meaning beta Jz is larger than 1. You have 3 solutions, right? While when t is less than equal to tc, then you have just one solution, namely m is equal to 0.
Should be greater than equal to, right?
What? Sorry, I beg your pardon. Sorry. Obviously. Sorry. Fine. But this is just at the level of an equation, roots, nothing more. I cannot say phase transition. And so when we come back after Puja vacation, we'll have to compute the free energy of this quantity within the mean field of this system, within the mean field approximation. I know the partition function. The partition function is what? So this is the partition function. I know the partition function. What I have to do is that I have to find the free energy. I have to take the derivative with respect to the free energy and show that the second derivative of the free energy diverges when beta c is equal to 1 over jz. I have to show that the second derivative of the free energy diverges when beta c equal to 1 by jz to be able to say that there is a second order phase transition at this temperature. At the moment, I cannot say anything. It's just some solution. 3 solution, 1 solution. That's it. Good.
Yes, sir.
Okay. And, just to preempt, I mean, of these 3 solutions, so there are 3 solutions. But what we will find is that we'll find the free energy. And you remember, only those solutions are acceptable that minimize the free energy. You will find that out of these 3 solutions, which is plus, minus, ms and 0, you will find that the 0 solution is unacceptable because it maximizes the free energy. So this is unacceptable. Second law of thermodynamics will kill you. We say, look, we say that the solution, the physically acceptable solution, has to minimize the free energy. This will not minimize the free energy. Only these will minimize the free energy. Therefore, we have to find the free energy to proceed. With this knowledge, you cannot say there is because phase transition, please to appreciate, it's a very, very deep concept. It's not like bifurcation. Bifurcation is you have a differential equation that has 1 solution or 3 solutions or 5 solutions. You say there's a bifurcation. Phase transition means you have to have a singularity. You have to have a singularity in the derivatives of the free energy. First derivative, second derivative, third derivative. Depending on it, you call it a first order phase transition, second order. So long as you are unable to find a singularity, a divergence, you cannot call it a phase transition. So that's why phase transitions are so difficult to study, because you have to work so hard to decide on whether it's a phase transition or not. Right?
So does the other 2 solutions have some physical meaning? I mean, except the free energy. Using the free energy, you can just eradicate the solutions. But if we think of the other terms, like, is there any physical consequence of the other 2 solutions?
No. These are the acceptable solutions. These are what you see experimentally, because they minimize the free energy. So if the system is in equilibrium at a temperature smaller than Tc, this is this, and these are the solutions that appear in that plot. M versus T. So when T is larger than Tc, you have only 1 solution. This is plus Ms, this is minus Ms. M equal to 0 is not a solution when T is smaller than Tc. Does that answer your question?
Yes.
These are the equilibrium magnetization. You get 2 symmetric solutions simply because your system has this up-down symmetry. Because SI, SJ, it's up, down. So you make all the spins up from up to down, and then the Hamiltonian doesn't change. So that's why you get 2 symmetric solutions. Also, tan hyperbolic x, it has this symmetry, that x going to minus x. tan hyperbolic x, it goes to minus tan hyperbolic x and so on. Okay?
Yes, sir.
Okay, fine. So let me take take the attendance while I wish you all happy Durga Puja and Dasera, Dasera and so on. So I hope you have some plans for going out and doing something. At least you all are. You will be staying in Calcutta, or like are you going out to visit your friends? No, I mean not Calcutta. I guess you know. Not all of you are from Calcutta, so whichever is your respective like city or town. Like, are you all going back, or maybe you are already there? Let me stop the recording.